But nobody wants to solve the eigenvalue problem. So I want to simplify the model further. If the mode spacing omega m is much smaller than the bandwidth, which is usually true, okay, mode spacing depends on your cavity length and your modulation frequency, which is usually maybe 100 megahertz. But your bandwidth is maybe terahertz or hundreds of gigahertz. So usually this is true. So imagine that in your underlying your spectrum, there are very dense modes. The spacing is very small compared with the bandwidth. So discrete modes actually approach a continuous spectrum, right? 只要那个间距太密了，你就把它当作连续的就好。Then E sub n originally is a vector with a lot of discrete unknowns. Now becomes a single unknown spectrum, big A of omega, continuous spectrum. 所以我不再需要解无穷多个 phasor， 我就解一个未知的光谱就好了。Okay? Your mode spacing becomes d omega, the frequency increment in calculus. And the n times omega m is the frequency of the nth mode, now becomes the continuous variable, omega itself. Okay? So whenever you see En, omega m, n times omega m in the previous model, you just replace them by A of omega, d omega, and the omega. Then you got this. This is the result. Okay. Still pretty ugly, right? But we can further simplify. Here I just highlight what happens. N squared omega m squared, so we use the third one. So you got omega squared in the new form. Omega m squared becomes d omega squared according to the second condition. Further simplification comes from this. This is actually the second order derivative of continuous spectrum, big A, right? If d omega is close to 0, this is second order time derivative, right? 这个 OK 吗？有没有人不知道这个？微积分嘛，一阶微分就是 difference quotient 取极限。做2次就变它，这就是2次微分。Okay. Then we actually arrive at a differential equation like this. Now it's better. It looks better, at least better than the eigenvalue problem, right? So it's pretty amazing, right? Starting with a very complicated system and ending up with a differential equation. And it's a second order ordinary differential equation, right? So supposedly the solution could be exponential function, damped oscillation, like something like that, right? But you are wrong. This is not the standard second order linearly ordinary differential equation that you have been familiar with. So the solution is not something you expect. Right. So what's wrong? Here. Unfortunate. Omega is your variable. When you see omega square, okay, something bad happens. Besides, G is not a constant, not a given constant. It's an unknown. You have to solve it along with the differential equation. So you still see the shadow of eigenvalue problem, right? You cannot just solve A of omega. You have to solve A of omega and the G simultaneously. Okay, so this is nothing like your damped oscillation solutions. Okay, but we are not so good in mathematics. We don't intend to solve it directly. We just want to borrow something well developed in other places. So what is that? One-dimensional Schrödinger equation with quadratic potential well. If you major in physics, you should be familiar with this topic, right? This is the 1D Schrödinger equation. This is your quadratic potential well, right? And you have seen this one in quantum physics. And you can compare them. Actually, they are almost the same. So the solutions found here should be solutions we need, right? But I have to explain the meanings of the terms in this equation. As I mentioned, this is your potential, quadratic potential well, okay? And what is your unknown function? It's a wave function of a particle in quantum physics, okay? So although this is actin-Molac laser, this is from the quantum physics, but they share the common feature. And mathematically, they share the same solutions, okay? So I just borrow what we can find from solutions to one-dimensional Schrödinger equation with quadratic potential well. You have permitted energies, right? Discrete permitted energies. E sub nu equals 2 nu plus 1, which is some integer, odd integer, times a basic number, E0, determined by the corresponding coefficients. Okay? You have permitted wave functions or eigenfunctions, which is a Hermite-Gaussian function, a Hermite polynomial, New's order Hermite polynomial times a Gaussian, right? It's well known in quantum physics. And this is the plot. The purple dashed curve means the quadratic potential well, and the E0, E1, E2 are the first 3 permitted energies. E0 is the fundamental energy, okay? It's not 0. And for every other permitted energies, they are spaced by the same amount, E0, 2E0, okay? And the blue curve is the fundamental mode of permitted wave function. The green one is the first higher order mode. The red one is the second higher order mode. The cyan one is the third higher order mode. They are Hermite-Gaussian functions. Okay. So for the same reason, you just compare the coefficients and borrowing the solutions to the Schrödinger equation we have seen in last slide. Now you can have permitted gain spectral peaks. Remember, G, the saturated gain coefficient, is the eigenvalue we want to solve. Now we know there is not just one G, there are infinitely many permitted G values. G sub nu, the New's order of your permitted gain spectral peak, is equal to L, your cavity loss, plus 2 nu plus 1, an integer, times delta G, a constant, and the delta G is like this, obtained by comparing the coefficients between the Schrödinger equation and the equation we derived for actin-Molac. Okay? Besides, we have permitted pulse spectra, eigenfunctions. They are also Hermite-Gaussian functions. A sub nu of omega means the spectrum of the New's permitted pulse spectrum in actin-Molac laser. Remember, it's a frequency domain function, frequency domain solution. omega is spectrum, right? So spectrum is Hermite-Gaussian. Time domain is not Hermite-Gaussian. Just be careful, okay? And the gamma coefficient is determined here. And you know gamma actually means your pulse width, right? According to our previous section. Your time domain is a Gaussian, so your frequency domain is also a Gaussian, and you can write down the formula of pulse width. It's proportional to square root of gamma. And now, according to our second approach, we can solve gamma. Okay? And you can compare the result in section 2-2. At that time, we use Gaussian pulse model. We also solve gamma. And actually, they are the same. So with two different approaches, either a Gaussian pulse model or coupled equations, you arrive at the same result. The pulse width formula is the same. Okay. So some remarks. What we have obtained in the first approach, the Gaussian pulse approach, is actually a spatial case, the fundamental mode only. So in frequency domain, you have a Gaussian spectrum because Hermite polynomial is a constant. Zeroth order is constant. Okay? Your time domain is also a Gaussian. But if you observe the temporal intensities of higher order modes, okay, I sub nu of t, nu is larger than or greater than or equal to 1, they always have two peaks. Okay? So fundamental mode is a spatial case. This is the first higher order mode. The upper one is your spectrum, which is first order Hermite Gaussian function. But the bottom one is the time domain intensity distribution, which has a double peak structure, right? If you observe the second higher order mode, you have a different Hermite Gaussian spectrum, more peaks, right? The green one has 1, 2, but the red one has 1, 2, 3, right? Even higher, you have 1, 2, 3, 4. You have more and more peaks in frequency domain. But you always have double peaks in time domain. These are the corresponding time domain structure. Although they are different, but they always exhibit just two peaks in time domain. So be careful. Although in the frequency domain, as your mode number is greater and greater, you have more and more peaks under your expectation, but in time domain, it's not like that. You need to perform inverse Fourier transform to get these time domain features. Okay? And more importantly, because you might have one question, according to mathematics, I have not just one solution, I have infinitely many solutions, right? Then, can I observe all these solutions in practice? Right, it's a matter about the effective gain or effective loss. Say the effective loss of the news mode is G sub nu, right? According to the concept, gain equals loss in steady state. So if the news mode has a saturated gain spectral peak G sub nu, the effective loss has to be the same. And you can see the higher the mode, the older, you have bigger nu, you have a bigger effective loss. So higher order modes, although they are self-consistent, but they are unstable. They will die off in steady state. So what does this mean? Self-consistent. That means all these solutions satisfied with the self-consistency condition. So if you send something like this into your active Monarch laser cavity, they will survive if there is no perturbation. So after round trips remains the same. It satisfies with self-consistent. But they are not stable. It means whenever there is a noise perturbing your field, it's no longer exactly the first higher order mode. Then you need projection, right, to the first order, zeroth order, and even higher order. Then when that happens, the zeroth order component corresponds to smaller effective loss. So after many round trips, it will survive. On the other hand, all the other projections will die off because they see higher effective loss. So in practice, you cannot observe them. Self-consistent, but not stable. So that's why you always observe this, the fundamental solution, a Gaussian pulse. Okay. I think the best way to verify this statement is just use numerical simulation. You can write the computer code simulating the active Monarch laser, and you send an initial condition like this with a little bit noise component. Then after some round trips, you can observe it will evolve into this one, and this will not exist in steady state. Okay. But if you send an input like this, even with a noise, it doesn't matter, it will survive. It corresponds to the lowest effective loss.这些 GV 都是 steady state 算出来的。
所以说你一开始材料就是一定要是特定的 G， 还有特定的 V 才可以。
起始条件不用，起始条件你一开始的 G 叫做 small signal gain， 跟你的 pump 有关而已。每一个 mode 看到的 maybe 都是。
可是你现在是Schrödinger equation解，就是你去镜子解出来的一个Schrödinger equation， 它是有，因为你能量不延续，所以它现在的那个现在右边的那一项，它是一定要有特征的能量才可以出来。然后可是你把它仿造的话，表示你一定要有特征的G才可以把才可以就是。
是指那些 discrete 的 G 可以到 steady state 啊，不代表我一开始就要是这其中之一，不用啊，我一开始随便给他一个 G， 不在这些没关系，我的 small signal gain 可以随便给，但是他自己会去运作，然后你发光之后，你的 G 就开始改了，对不对？一发光 G 会下降啊 ，gain saturation， 会降到最后就是到了 steady state， 只有这些 discrete 的值。可以满足 self-consistent， 那除了满足 self-consistent， 还要满足这个 stable 的话，那只剩 fundamental mode， 只有那个 G sub zero 那一个 term 会活下来，它会一路演化到那里去。你起始条件不需要是它们其中之一。Okay. So we have finished lesson 2. Here are some questions that you can try to answer. How to calculate the width and amplitude of a steady state active Monarch pulse? We introduced 2 different approaches. The first one is quick, but with some drawbacks. The second one is more complicated, but more complete. The difference is the second approach can answer you some important questions. Why is Gaussian? right? How the phases are locked together. Okay. Second question, why is the steady state pulse nearly Gaussian? And when will the Gaussian approximation fail? Why is Gaussian? In the first approach, it's a smart guess. Just we expect if you want to meet self-consistency, you need Gaussian. Because Gaussian multiplies with Gaussian is still Gaussian. Fourier transform of Gaussian is still Gaussian. Without this property, you can hardly expect you can have self-consistency. Okay, it's a matter of smart guess. But in the second approach, things are more clear. It's Gaussian because it's a special case of Hermite-Gaussian solutions. It's only a fundamental mode of Hermite-Gaussians. Okay? When will the Gaussian approximation fail? You have to verify what assumptions did we make when we arrive at the Gaussian solution. At least you need to remember the gain bandwidth compared with your steady state spectrum has to be much broader. Your pulse width compared with your modulation period has to be much narrower. Okay? So the assumptions are very important because in the future, when you try to borrow the formulas you arrive at, don't forget about the assumptions. If your working conditions are in violation with those assumptions, you can no longer use those formulas. Okay. 是常常落进的陷阱。这公式太有名了，拿到就用。连你的工作条件违反了，你都忘了去检查，就是你算出来的结果根本就不能用。Okay. Third, why can the loss modulation lock the phases of different longitudinal modes? It's a very important question. Why these phases are locked together?
Energy interchange.
Yes, the key word is energy transfer from the central mode to the neighboring modes by way of loss modulator, right? Why don't the higher order Hermite-Gaussian modes survive in steady state? Mathematically, they are there, but why can't we observe them in steady state?
They are unstable.
They are unstable, but what's the meaning of unstable?
Noise can make them change into the basic.
I try to convince you in this way, but I suggest you to verify numerically. Do not just trust my statement. Maybe after simulation, you got something different. Try to approach me. I will give you bonus points. If you prove me I'm wrong, give you a pro. 那要挑战权威啊，不要相信权威啊。你真的算出不一样的事，赶快找我。Maybe we can write a paper, right? To astonish this research community. Okay, you are wrong. Everyone is wrong. We find something different. Okay, 就自己去检验啊。但是简单的比喻是这个样子。实物上不可能没有 noise. Whenever you have noise, you are slightly deviated from the mode solution. 就好像一个向量，对不对？你如果是某一个 mode， 就代表你是某一个正交向量嘛。现在有 noise， 它就偏了一点点。一旦它偏了一点点，是不是它可以投影到所有其他的正交，有一点点的分量？好，这些分量就要开始彼此去竞争了，丢在这个 cavity 里面去 compete。Initially， 你的那个起始条件的 mode 可能占最大比例，可是 maybe 几个 round trips 之后 ，energy 都搬到那个 loss 比较小的，所以那一个向量越长越长啊，你原来很长的向量越来越短，最后就跑到那里去了。好，这个就是你的 noise 会 ruin higher order modes 的原因。The picture is like this.